Welcome back everyone. In the previous unit, we learned about the diode equations. So diode equations tells us mathematically the relationship between the current that flows through the diode and the corresponding voltage across the diode. So that is our diode equation. ID is equal to IS e to the power VD over NVT minus 1. And it consists of two parts. One is the diffusion current part and another one is the drift current part. And the diffusion current part, which is occurring in forward biased region, we can see that this is an exponential function. So that is very consistent with our observation of the graph. So the curve also looks like an exponential curve. Now, if you go for an approximation, so that means if we ignore the drift current component, we get the simplest form of diode equation, which is ID equal to IS e to the power VD over NVT. So this unit, we're going to discuss about the different diode models. And models are used to analyze device circuit in a convenient way. Of course, when you're going to use a model, we're going to get very approximate value of the circuit. However, this amount of error that we're going to obtain or the accuracy you're going to lose, we can live with that. On the other hand, it is really difficult or complicated to use the real characteristics. For example, for diode, we know diode IV characteristics exponential curve. So which means it's a non-linear curve. And in order to find the current through the diode and the voltage across the diode, so you have to go through a very rigorous process, which is often requires a computer programming to get the exact value of the current and the voltage of the diode. So this way you're going to learn about three types of model. One of them is piecewise linear model. Let's go over these things with an example. Let's say there is a simple circuit, series circuit, where there is a voltage V is equal to 10 volt and the resistance R 2K and the diode. Now we used to determine the voltage across the diode, which is VD, and the current through the diode ID. So let's say the current that flows through the diode is ID and the voltage across the diode is VD in that circuit. Now you can, of course, you can imagine that the value of VD and ID will change if you change this parameter. For example, instead of 10 volt, if you use 20 volt, you would get different current, different voltage. So let's say at 10 volt, we got ID and VD, and let's say, so this is the, on the curve, this is the value of voltage and the current for that circuit. And we call this thing Q point. It's a Q. And this curve is on the IV characteristics curve, which is the black line, which is the real IV characteristics. Now we can do one thing. We can replace these IV characteristics with two straight lines. We can go for this approximation. So that means if you draw one straight line from here to here, and so this is another straight line, you see the both characteristics, the real IV characteristics and the one with two straight lines, almost identical apart from this region. So whatever the errors or whatever the losing in accuracy we're going to obtain here. And I think we can live with that. So let's see. So Q is the voltage and the current of the diode in that circuit. And we draw a perpendicular line QR, and OR is the voltage and QR is the current. And this straight line intersect the x-axis at point P. And then point P from origin is measured VD naught. Now, since this is a straight line, and we already learned that if you ever notice any straight line in any IV characteristics, it must indicate that there must be a resistance inside the device. So there is a resistance. And this resistance, we call it RD. This is the diode internal resistance. So, diode internal resistance. M is the slope of the straight line, which is 1 over RD. Let's do a little bit of geometry, where OR equals to OP plus PR, where OP already learned that VD naught plus PR, which is our VD, which is OR. And then if you go to this triangle PQR, it is a right angle triangle. So in that case, the slope M, which is 1 over RD, is QR divided by PR. QR is ID and then PR. So from there, we can find out PR equals to ID RD. Now, if we put the value of PR here, then we find out VD is equal to VD naught plus ID RD. So this is the relationship between the current that flows through the diode and the voltage across the diode. If you consider the diode IV characteristics is nothing but two straight line. So that's why it is called piecewise linear model. Now, if you compare this relationship with the real IV characteristics, which is ID, IS, e to the power, VD over and VT. So notice this one is exponential and this one is linear. As a human being, we always like to straight things up. So we find it convenient if we can straight things up. Now, next we're going to see how we can obtain an equivalent circuit. So for that, let's say we have an equation that was obtained from a KVL, which is E is equal to I R1 plus R2. So by looking into this equation, you can, even in you close your eyes, you can see this is a KVL from a series circuit, and that looks like this. So DC voltage source and R1 and R2 are in series, and the current is flowing through is I. So the thing that I want to show it to you was that if you have an equation, from this equation, we can draw the corresponding circuit. Now let's say we add in this equation a V1, which means a DC voltage source. So if you add a V1, in that case, the corresponding circuit should look like this. E is equal to V1, R1, R2 are in series, and the current is I. So if you go back, if you do the KVL, you would get this KVL equation. So that means equation to circuit And I can also go from circuit to equation. So going from equation to corresponding circuit. Now, if we go back to our previous circuit, so where we had in one circuit we had the diode, which is the part of the circuit, and we have the current flowing through this diode, which is ID, and the voltage across the diode is VD. After doing this approximation, we obtain this relationship: VD is equal to VD naught plus ID RD. And then what we learned from here, so that means from equation, we can go to a equivalent circuit. So that means if we draw the equivalent circuit, so this circuit, this equation gives us the circuit looks like that: a DC voltage source and a resistance in series. So from real circuit, we got the approximation. From approximation, we obtain the model. So for example, we found out the VD naught is 0.6 volt and RD equals to 10 ohm. So in that case, in that circuit, if we replace the diode with a DC voltage source and a resistor in series, where DC voltage source is 0.6 and the value of resistance is 10 ohm, then we got then it becomes a very simple circuit, where ID is equal to VD minus VD naught divided by R plus RD, and this is so that is our piecewise linear model. And then we can even simplify the model that we have obtained. So that means if you notice, the value of the resistance RD is 10 ohm, which is generally quite small compared to the external resistance. In that case, we can ignore it. So if you ignore it, and if you go back to our previous equation for piecewise linear model, and if you put the value of RD is equal to 0, then we get VD is equal to VD naught. So that means in that case, we can replace the diode simply with a DC voltage source. So that means if we set this is 0, then our circuit, the current becomes ID is equal to VD minus VD naught divided by R. So this model is called constant voltage drop model. So how does the IV characteristics for constant voltage drop model looks like? Again, ID is the vertical axis current and VD is the horizontal axis or voltage. And if this is our piecewise linear model, which is replaced by two straight line. VD node is the intersection between the straight line and the x-axis. Now since we set RD is equal to 0 in constant voltage drop model, so we get our slope is equal to infinity. So that means this straight line is become vertically up straight line. So that is our constant voltage drop model IV characteristics. So then we can also go for another model where we can ignore the value of the voltage drop across the diode, which is we can set VD naught is equal to 0. Also, we already set RD is equal to 0. So that gives us the diode in the circuit, and which is VD is equal to VD naught plus ID RD from our piecewise linear equation. And if we set both of them to 0, so we get VD is equal to 0. And we can replace the diode in short circuit. So when in ideal diode model, when the diode is forward biased, we replace the diode with short circuit. And in that case, if you determine the current, it will be ID is equal to 10 divided by, so V divided by R. Now remember this, all the model that we have obtained, this is when the diode is in forward biased region. Piecewise linear model, constant voltage drop model, and the ideal diode model is valid as long as the diode is operating in forward bias region. Because the diode is off for all the models, when the diode is reverse bias, it is off. So we can replace the diode with open circuit. Now, the last thing, we're going to use the constant voltage drop model for most of the diode circuit analysis. Sometimes we'll be using ideal diode model, but we will not be using that much of piecewise linear model. And for constant voltage drop model, if we consider silicon diode, when it is forward biased, it is 0.7. So that means we're going to replace the diode with a DC voltage source of 0.7 when it is silicon diode. And if it is germanium diode, we're going to replace the diode with 0.3 when it is forward biased. Thank you.